a nice paper. It's kind of a review. So, oops, I killed the PowerPoint here for whatever reason. It's about deep learning for data-driven Earth system science, understanding processes. So, I liked it. It has some nice points that I myself wanted to learn about, and then I put it into a podcast. Maybe it'll be 2 podcasts. Makes some good points about how the speed of data collection is evolving, how computational power is evolving, how models are evolving, and yet there are limitations on what the models can do, especially when it comes to predictions, parameterizations, um, mismatches with observations, or even analyzing the data itself in terms of capturing the parameters, or yeah, improving parameters for the models, but also capturing the patterns. And there are some good examples that we'll look at. So it says deep learning, it's a perspective, deep learning and process understanding for data-driven Earth system science. Machine learning approaches are increasingly used to extract patterns and insights from the ever-increasing stream of geospatial data, but current approaches may not be optimal when system behavior is dominated by spatial or temporal context. Here, rather than amending classical machine learning, we argue that these contextual cues should be used as a part of deep learning, an approach that is able to extract spatiotemporal features automatically, because you want this whole process always to be autonomous. And we can do this to gain further process understanding of Earth system science problems, improving the predictive ability of seasonal forecasting and modeling of long-range spatial connections across multiple timescales, for example. The next step will be a hybrid modeling approach, coupling physical process models with the versatility of data-driven machine learning. So it's not arguing for replacing dynamic models with AI and deep learning and so on, machine learning, deep learning. In fact, we'll read a little bit about what is the difference between artificial intelligence, machine learning, and deep learning. And it's really arguing that you need to use the data to learn the processes that then have to be improved in the model, so that then models can get better at forecasting, and also combine data-driven models and dynamic models to achieve a higher payoff in terms of, let's say, predictive skills, right? I am going to, obviously, bits and pieces of the paper are going to be presented here. I'm going to just be brief as usual. The combination of unprecedented data sources, increased computational power, and the recent advances in statistical modeling and machine learning offer exciting new opportunities for expanding our knowledge about the Earth system from data. In particular, many tools are available from the fields of machine learning and artificial intelligence, but they need to be further developed and adapted to geoscientific analysis. Earth system science offers new opportunities, challenges, and methodological demands, in particular for recent research lines focusing on spatio-temporal context and uncertainties. So we'll look at a few boxes here. An Earth system model, Earth system, and so on need some definitions, which I'm not going to do here, but I have several podcasts and in fact a whole course on Earth system science for adaptation and mitigation and so on, that you can look up. System, basically, it's components that act together to do something that each component won't be able to do. The way I'm talking to you now, waving my hand, saying something, thinking, reading, recording. So this is a system. My hand by itself cannot do much unless it is attached to the rest of the system, and so on. So I'm just jumping ahead. At the same time, a deluge of Earth system data has become available, with storage volumes already well beyond dozens of petabytes and rapidly increasing transmission rates exceeding hundreds of terabytes per day. These data come from a plethora of sensors measuring states, fluxes, and intensive or time-space integrated variables representing 15 or more orders of temporal and spatial magnitude. Earth system science can go from molecular scales to planetary scales, so we have very large range. They include remote sensing from a few meters to hundreds of kilometers above the Earth, as well as in situ observations increasingly from autonomous sensors at and below the surface and in the atmosphere, many of which are further being complemented by citizen science observations. Now there is even genetic data being added to the mix, socio-economic data, not just physical data. Model simulation output adds to this deluge. Model simulation output adds to this deluge. The CMIP5 data set, so this is a bit older. Now we have CMIP6. So CMIP5 data set of the climate model intercomparison project, used extensively for scientific groundwork towards periodic climate assessments, is over 3 petabytes in size. And the next generation CMIP6 is estimated to reach up to 30 petabytes. Resolutions have been improved, more details added, carbon cycle, vegetation dynamics, dynamic vegetation, and so on. Data from models share many of the challenges and statistical properties of observational data, including many forms of uncertainties. In summary, Earth system data are exemplary of all 4 of the 4 V's that we'll see in a minute of big data: volume, velocity, variety, and veracity. One key challenge is to extract interpretable information and knowledge from this big data, possibly almost in real time, and integrating between disciplines. So sorry, I'm pulling the cord here and hopefully not destroying the recording. Taken together, our ability to collect and create data far outpaces our ability to sensibly assimilate, let alone understand it. Sensibly assimilate it, let alone understand it. Predictive ability in the last few decades has not increased apace with data availability. To get the most out of the explosive growth and diversity of Earth system data, we face 2 major tasks in the coming years. The first one is extracting knowledge from the data deluge itself, and secondly, deriving models that learn much more from data than traditional data assimilation approaches can, while still respecting our evolving understanding of nature's laws. So data assimilation, you may already know, is a blending of dynamic models with data, typically done for the past, to recreate gridded, dynamically interpolated data we call reanalysis, or you are doing data assimilation to initiate coupled models or weather models for weather prediction, climate prediction, and so on. But now we also do assimilation of biological data for deriving various parameters and constraining one thing with the other. So if you don't have productivity data, you can assimilate all the other data to constrain productivity, just as an example. Okay, so here is the 4 V's. Then we are looking at big data challenges in the geoscientific context. Sorry about that. Data size now exceeds 100 petabytes and is growing quasi-exponentially. Tapering of the figure to the right indicates the decreasing data size. So we need to take all that is available from data and models and produce information that is digestible. The speed of change exceeds 5 petabytes a year. That data are taken at frequencies of up to 10 hertz or more. Reprocessing and versioning are common challenges. Data sources can be 1 to 4 dimensional, spatially integrated from the organ level, such as leaves, to the global level. Earth has diverse observational systems, from remote sensing to in situ observations. The uncertainty of data can stem from observational errors or conceptual inconsistencies. There are lots of details, instrument error, representativity error, and so on. Let's just look at what is meant here. So we have observed and simulated big data. So volume, data size, petabytes, growing quasi exponentially. Velocity, the speed of change of the data platforms themselves. Volume of data, and the phenomena being observed. We never observed leaf scale area, leaf area index, chlorophyll, and various other things that can be combined to do amazing things. So things are changing at a very rapid speed. And variety, the diversity of data sources is now amazing, with drones and ships and aircrafts and satellites were there for a while, but now we have all sorts of autonomous vehicles, drones, and so on. And veracity, the uncertainty of the data. So what do you want to do? You want to extract knowledge from all this data. So it's kind of a schematic here on how we are doing the Earth system, and you want to understand patterns and extract knowledge. So small and digestible pieces of synthesized information has to be produced. Real-time critical in some areas, but not all. So you may be just watching how the forest is changing versus how to manage floods or wildfires and cyclones and so on. Integrated across disciplines. So it's not just about climate variables now, it's about vegetation, crop models, land use, impacts on people's livelihoods and so on. And you need to provide confidence and robustness so that you feed it back to the system, data from knowledge. So you want to say what other data and what scales and frequencies and duration, etc. are needed. So if you want to monitor for long term to observe changes in sea level and so on, versus looking at extreme events and so on and so forth, right? So that makes sense. What else are we going to do? Let's just look at state-of-the-art geoscientific machine learning, and then we have a long table that we'll look at. Machine learning is now a successful part of several research-driven and operational geoscientific processing schemes addressing the atmosphere, the land surface, and the ocean, and has co-evolved with data availability over the past decade. Early landmarks in classification of land cover and clouds emerged almost 30 years ago through the coincidence of high-resolution satellite data and the first revival of neural networks. Neural networks revival as applied to climate problems. Most major machine learning methodological development, for example, kernel method or random forests, very specific terms that we will leave for now. I'm not going to get into those details. Either you're an expert or you have to look it up, right? So the development has subsequently been applied to geoscience and remote sensing problems, often when data suitable for pertinent methods became available. Thus, machine learning has become a universal approach in geoscientific classification and change and anomaly detection problems. In the past few years, geoscience has begun to use deep learning to better exploit spatial and temporal structures in the data, features that would normally be problematic for traditional machine learning to extract. So we'll see what we mean by deep learning, that it can extract more than machine learning. I'm just taking bits of the text just to make the most salient points, according to me, very subjective. So you need to read the paper. It's a very nice paper and not at all very long, but still I don't want to read the whole paper. Notwithstanding the success of machine learning in the geosciences, important caveats and limitations have hampered its wider adoption and impact. A few pitfalls, such as the risk of naive extrapolation, sampling or other data biases, ignorance of confounding factors, interpretation of statistical association as causal relation. So this is always the danger with statistical approaches. Correlation doesn't mean causality. Or fundamental flaws in multiple hypothesis testing. It's called p-fishing, significance fishing expedition, where you put together all the data and you try to see what may come out. These should be avoided by best practice and expert intervention. More fundamentally, there are inherent limitations of machine learning approaches as applied at present. It is in this realm that the techniques of deep learning promise breakthroughs. Okay, so I'll leave this here and we'll come back and read about a few things. Lots of AI terminologies, which are details that I won't get into because first of all, I'm not such a big expert on it. Secondly, it's a bit of a digression of the main point of the paper, that deep learning brings something new to understanding Earth system science and improving predictions, and the proposed hybrid modeling, where you mix deep learning with dynamic models to get more bang for the bucks in terms of just the dynamic models can give and what just the data can give. So this is all about predictions, and of course you want to extend this eventually to somehow projections as well, but we'll just see what this paper does in terms of what it advocates. Okay, so we'll come back and continue the discussion on deep learning for Earth system science. Okay.